not intending on doing a lot of basic oscilloscope, how to use an oscilloscope. Although if we run out of time towards the end, which I'm afraid we might because we got an hour, well, 50 minutes, I'll be happy to go back over and cover basic oscilloscope usage. As I go, if you've got questions, feel free to let me know. In general, I tend to like my presentations to be interactive. Today I've got a handful of topics that I want to cover, and I'm hoping I'll have a lot of questions to cover the rest of the time. So essentially, what an oscilloscope is a voltmeter that goes and provides a time element. And so it allows you to go and take a look at a signal on your system that is changing with time. A lot of times what you'll find is, for example, you've got some serial communications that you're trying to do, and it simply isn't working. And there's a number of different things that may be wrong. You may have your transmit and receive lines reversed. You might not have gotten the serial ports set up, so you don't have any signals at all. Well, how do you determine that? Putting a scope on it, putting a regular voltmeter on it is not going to do you any good, because if it's working, the signals are going to be too fast for a scope to show you anything. For a meter to show anything. And that's where you use a scope. And so what you'll do is go and attach your leads and take a look. Very simple. And usually you'll find out in pretty much a heartbeat whether you've got signal. Typically what I'll do is, when I'm hooking something up, such as serial connection, before I actually hook the wires, I'll go ahead and scope out both transmit and receive pins to make sure that I really didn't get my, shall we say, my wires crossed. It happens all too often. In general, a lot of documentation for devices isn't always perfectly clear on which pins transmit and receive. And it's like, okay, you've got two devices, which transmit goes to which receive, and you want to make sure you get those right. Fortunately, most devices, if you get them backwards, they just don't work. They don't blow up. But if you're going and trying to transmit on a pin you thought was receive, or if you're trying to receive on a pin you thought was transmit, anyway, if you've got your wires crossed, if you go and scope out a transmit pin, but it turns out it's actually a receive pin, on your scope, all you'll end up with is a straight line. Immediately you know, okay, I've got one of two problems. Either I'm on the wrong pin, or I haven't got my serial port running correctly. Once you do have it set up properly, essentially what you'll end up with is, basically a square wave pattern. It will usually be a very irregular pattern. Oops, well, that one's square, not round. And it becomes very obvious very quick that yes, I am properly on the transmit pin. Let's see. Another thing that you will frequently want to do with a scope is go and check your power supply pins. What happens to a circuit if you don't have good power? Very quickly, your system will become erratic or flat, not work. One thing that you may do, for example, during the show and tell, I was showing off my little handy dandy little voltage regulator. Well, like I say, this particular one it'll output an amp. What's going to happen when I pull an amp and a half? If you pull an amp and a half from an older linear regulator, you may very well simply smoke the regulator. Typically with the switching regulators, they're a little bit smarter, And what'll happen is, instead of going and dying, what they'll do is go into what's called foldback mode. And basically that's a fancy word for, it's gonna drop the output voltage to keep from damaging itself, or it may simply shut off. And so an easy way to find out what's going on there is you go and you measure the voltage. Now this isn't necessarily strictly a scope method. This will actually work with a meter as well. But if you've got a circuit that goes and has a variable current draw, where maybe you go and run a servo, and that servo only runs periodically, and it works most of the time, but maybe you have some other circuit that you're also run sometimes at the same time, what you'll end up with two devices that use different amounts of current that occasionally between two of them exceed your circuit voltage. And at that point, what you will actually see on your scope is you'll see your voltage going along, assume that's a nice straight line, but every now and then when you exceed the current, you may very well see this output voltage go a dip. And that's one indication that you've got power supply problems. Specifically, that you may very well be pulling more current than your supply will provide. That's something that is very hard to catch in some cases because it only happens occasionally. And everybody that's done any significant troubleshooting very quickly discovers that those problems that happen every now and then are by far the most aggravating. Let's see, what other kinds of troubleshooting? Let's see, you've got motor noise problems that you can sometimes find with the scope. Those are very tricky. I was planning on going and trying to duplicate some of those and create some problems to show with that, but well, I wasn't able to actually cause the problem, so I can't demonstrate that. Oops. Let's see.
But your last project had a lot of noise.
I'm sorry, what?
Your last project that you brought in had a lot of noise. Remember what was making that?
Well, that was actually mechanical
Okay.
noise. The gear motors and everything were just, they made more noise in a perfectly quiet room, so you shut me. Let's see. One question that I got over email that is a problem. It's not really so much a troubleshooting your circuit problem as a troubleshooting your scope problem. With digital scopes, as opposed to the older fashioned purely analog scopes, which typically are tube type scopes, and they're usually, you have a scope that's about this big, except it's about this deep. It's actually got a tube in it. When you're going and dealing with fast signals with a tube scope, you see an actual completely honest analog signal. So you very seldom have problems with having the scope tell you one thing when really it's something else. And with digital scopes, what they're doing is it actually goes and on a very regular basis, it goes and samples your input voltage. And this works very well as long as you don't have the scope set up incorrectly. If you have a scope set up incorrectly, it will lie to you. This lie is called aliasing. And it's a concept that a lot of people have a lot of trouble with. I did too. I spent a lot of time looking this over and trying to figure out, okay, what exactly is aliasing and how the heck do I explain it to somebody else? And I finally got it sorted out with the help of a website whose name unfortunately has escaped me again. But they had a wonderful little graphic on their webpage. And I encourage everybody to go and Google oscilloscope aliasing because it has a lot more detail than I will be able to provide here. But aliasing comes up as a problem when you have the time base of the scope set wrong. Because you can end up having a signal that looks different from what it really is. Let's say you have a signal that comes along. See if I can actually get this drawn properly the first time. Let's say you have a signal that's sitting here like this. You know, the scope will go and sample the signal here, and it'll sample it here, and it'll sample it here. You know, each one of these ticks, it goes and samples the signal. When you've got this set up right, you end up with a perfect signal. The problem that you can come up with, let's see what I do here. Did I end up with this wrong again?
Well, that looks right from here, but what you need to do is make a sine wave that is much
Noisier.
faster and basically
Yeah.
You want a smaller signal relative to
complete
tick
the
size.
cycle between the ticks.
Yeah, I think I've got too
Try
many.
high frequency.
I've got too many pips here. That's what it is. Oops. Wait a minute. All right, let me start over here. All right. So let's say we sample here, 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 here. Assume those are nice, evenly spaced samples. So you've got here you've got several samples during the cycle, and so it goes and provides you a reasonably accurate representation of the signal. However, if your actual signal comes along, God, I knew I should have printed this out.
Use a
last
high
night.
frequency if you want to show aliasing.
You've got a signal that comes along like this.
Yeah, put out all zeros.
Essentially what's going to happen is it's not going to show it properly because every time that it samples, you're actually at 0 voltage. Or it may be that every time it samples, you're at some voltage. And what the scope will do is go and try and fit a curve that matches those points, and it won't find it. So you have to go and make sure that you understand what the frequency is of the signal that you're trying to read, and make sure that you set your scope so that you end up with a time base that provides a good sample, a number of samples during that time. Let's see.
So can you just?
When you start dealing with scopes, and in fact, even when you're dealing with microcontrollers at any point, you pretty much need to understand this formula. Now, what this formula is it tells you the period of a signal is the frequency divided by 1, or 1 divided by the frequency. And what this does, it allows you to go and convert a frequency, the number of times something happens in a second, to how long that is. So let's say, let's say you have a signal that's, 1,000 hertz. And you want to go and figure out, okay, how do I set my scope up properly to go and display a 1,000 hertz signal? Well, you need to figure out, what's the period of that, and the period will be, 1 divided by 1,000, or 0.00, 0.01.
Wait. You mean we're not just supposed to keep flipping the dial until we see something show up on the scope?
Well, yeah, you can do it that way, but if you stop at the wrong point, your scope will be lying to you. And if all you want to do is actually see what the signal looks like, that might work. But if you're going to go and actually do some measurements to make sure exactly what the signal, what the frequency of the signal is, you need to set it up properly. So anyway, if you want to know the period of a 1,000 hertz signal, you have 1 divided by 1,000, or 0.001, or it's also known as 1 millisecond. And a good way to set your scope up for that would be you set your scope for 1 millisecond per division. That way you'll have, quite a few cycles on the scope that are being displayed. Maybe you set it up a little bit faster so that each cycle is displayed larger on your screen. Okay, so who all is completely lost here now? Am I the only one that's lost? No, okay. Let's see.
What's the disadvantage of setting the scope up so that you're always at a very fine, a very high sample rate? There's got to be a disadvantage to that, right?
Oh, absolutely. Your screen ends up showing such a small part of the signal that it doesn't make sense.
Oh, okay.
You don't, with scopes, even with the digital scopes, for example, you don't actually directly set the sample rate. You don't set that clock that it goes and takes samples. Although internally, the scope may go and change that depending on what your other settings are. What you'll actually do is you'll set the speed of the scope as to the period per division on the screen. Now I know a lot of people probably are not going to be able to see this very clearly. Who here is familiar with what a scope screen looks like? Okay, who's not familiar? Okay. Well, essentially you've got your scope screen, and it's divided into a whole bunch of divisions, and all you want to do is set your scope. How long does it take? What period of time does this division show? And that's back to this formula. When you're dealing with scopes, you really pretty much need to have at least a fairly good grasp of this. And one thing that I learned in electronics course is how to deal with formulas, especially something simple like this. It's simple. If you need to figure out one of them, you just do this. You cover up the one that you're looking for, and you can go and take 1 divide p by it to get the frequency, or you can go the other way around. Very handy. If you don't grasp that thoroughly, this won't make sense.
I think a real easy way to do all that is just set the sweep up. If you got totally unknown signal, crank your sweep up as fast as it goes, and you'll get just some line. Keep backing off until it starts showing the signal. If you do it the other way around, starting really, really slow, that's where you're going to get aliasing. As you start stepping up, you get aliasing first, because the sweep time is too slow and your sample rate is too long between samples. And as you go up, you'll eventually see something, but it may be wrong, because it may be an alias. But if you do it the other way around, start at the highest sweep rate, you're not going to get any aliasing to there, and keep backing it down until you see a reasonable waveform. At least that's the way I do it.
Okay, well, that pretty much wraps up my presentation.
So what's the difference between?
Yeah, you're right, Dale. That would work. That would solve the problem exactly. Is you start with a very fast sweep rate, and you just start turning it down until your signal shows up, and that you won't, like Dale says, you won't show the aliasing, because the aliasing is where you've got a slow sweep and a fast signal.
So what's the difference between? I've seen lots of digital scopes. They have 3 settings for the sweep. Obviously, the single is you just get a one-shot capture. There's the sweep and then normal. I never knew, and whenever I go to normal and sweep, the difference, I don't see anything ever change on.
There's a sweep and a normal?
Yeah.
Auto, normal, and one shot, I think.
Yeah.
Auto triggers anytime. Normal triggers off of your threshold of your trigger point.
Well, that would be your one shot.
No.
I can
Repeat.
explain this.
Okay, good.
All right. One shot, you arm the thing, and it sits there ready for the trigger, and when the trigger happens, makes one trace and it stops, and you have to reset it again. Auto, even if there's no trigger at all, it'll say, okay, there's no signal for so many, whatever time period, it'll sweep again. It just sweeps by itself. And when a signal appears, then it'll lock onto it and try and synchronize with it. But if there's no signal, it'll continue to sweep. Or if there's no signal large enough to trigger the thing, like a really small signal, it'll still show you some unsynchronized wiggling on your trace there, but it may not be synchronized. Auto shows you nothing until it actually,
No, that's.
normal shows you nothing until it actually gets a trigger.
Okay.
It doesn't, it's no sweeping whatsoever until it sees a trigger, then it sweeps. Then it waits, another trigger, sweep. So it's like one shot, but it automatically resets.
Okay, all right, that makes sense, because I was never able to see a difference, but I always had my trigger set up, so that's probably why. But also on the triggers, I know the difference between AC and DC coupling on your signals and everything, but the trigger on a lot of digital scopes I use also has an AC and DC option for the
Right.
trigger, but I figure your trigger level is a level on your screen somewhere, no matter what.
Well, it's typically a voltage point that,
But that voltage point, if it's AC or DC, it's still voltage.
Well, if
so
you've got some AC signal say you got 5 volts and it's got 1 volt of ripple on it. And you have to move your trigger point up to near 5 volts in order for it to start triggering on that 1 volt ripple. If you set the trigger coupling to AC, it'll ignore that DC offset. Doesn't matter what the DC offset is, it'll trigger on that 1 volt.
okay.
It's just like if a capacitor in series with the signal and the trigger. Whereas DC, it's DC coupled from the signal to the trigger.
Okay. Got it. Those are my questions. I didn't bring any
Good.
more.
good.
How do you know if you're at 1,000 hertz? I mean, are you looking at your, are you reading it from something else, or are you looking at your sheets, your spec sheets?
Try just taking.
Typically, you'll have some idea of what signal you're looking for. Hopefully by the time you've got things together to the point where you've got your scope going and you're trying to diagnose what's wrong, you should generally have an idea within your circuit of what to expect where.
Okay.
There may be some places where you've got, some signal that is just completely unknown. But most of the time, you should have a pretty good idea of what to expect. And so you go and set things up from there.
Your formula right there explains it to her. 1/1000 gives you 1 millisecond.
Well, yeah, but
Your division.
I know, but I'm saying that
Yeah, but
when
she-
I build a circuit, how do I know what the hertz is?
That's what I'm trying to tell you.
Well, no,
You use the
no.
oscilloscope to tell
What
you.
she's asking is, where do I get this 1,000 hertz that I'm looking for to start with? I don't, she doesn't know the period and she doesn't know the frequency. How does she know? Well, the
Scope.
answer is,
Scope.
hopefully you'll start off knowing, but if not, Dale's method works perfectly. You start with your scope at the highest, and you
Turn
start
it
turning
down.
the time base down until a signal shows up, and then in the old days, we would go and turn it down, and then we'd look at the sweep rate and look at the divisions on the scope, and go and count it out, find the period, and then we'd go and run it through the formula, and we'd know the frequency. Now you just push your button, it just tells you.
I think a more general answer is it's what technology you're working on. For example, if you're working on I2C, you know it's going to be around I2C's frequency. You can just look at what I2C's frequency is, and so you know to expect that frequency. So go ahead and set my equipment to that range.
So that would go back to the spec sheets.
Right.
Yeah.
Same with your
I know the
PWM
oscillator
of your
circuit's
motor.
about 1,000
If
hertz.
you want to see your
But
pulse
my
width
parts
modulation
have-
signal.
Okay,
My
I
parts
hear
have, 2%,
too.
sorry.
5% variance, so I'm gonna be somewhere around 1,000 hertz, but
Right.
how do I find out exactly what that oscillator is putting out using the scope? It could be
Okay.
putting out 990,
Well-
it could be putting out 1,010.
Yeah, well, okay, let's say you're building an oscillator that ideally is 1,000 hertz.
On paper, it should be
Yeah.
putting out 1,000 hertz.
So, you go back, let me draw this a little bit bigger. What you'll do you'll have your scope screen. I'm going to assume that you're using a good old-fashioned dumb scope. Because it's too easy, you know, the easy answer is if you use a digital scope, you get it on the screen, you push the button, it tells you, you know, it's $9.98. That's
Yeah,
too easy. How do you act, now, how do you do this if you're stuck using a, you know, like a military scope that's from
I know, you
1940?
get analog scope right there.
Actually, I drew this in the wrong way. I need it long, not tall.
There's that scope right there, and also has a spectrum analyzer
Yeah.
function. You can just observe and see all the frequencies.
There's a measurement button
Nice.
when you're talking, where you can choose what kind of information you want to display numerically. You can do things like peak voltage, amplitude voltage, frequency, period, on duty cycle, off duty cycle. That advanced scope there has all those kind of abilities. That you can hold usually up to 4 different variables on the side of the screen to show you different things that you can specify you want to see.
Ooh, color traces.
Well, it's a color scope.
Yep.
You guys have all these fancy.
Of course, now I gotta stand back here so you can actually see it. Okay, well, let's say you have your scope set up to 1 millisecond per division. Okay, this doesn't work exactly for your example, but we'll get there. So what we have here, we have our scope set for 1 millisecond per division. So that means for every division, that's 1 millisecond. So the information that we can get from this trace right here is, and let's see, we'll say we're also set for 1 volt per division. So now all the information we can get from this is we can tell that we have a signal that is, it's a 2 volt signal because we're going up 2 divisions. We're high for 2 divisions, low for 2 divisions. So now we know, okay, well, we've got, you know, a signal that's high for 2 milliseconds, low for 2 milliseconds, high for 2 milliseconds. So now what we know is, okay, the total period of our signal, the period of the signal is from one point back to a duplicate of that same point. So we're gonna go and take the rising edges, and so we got one rising edge here, we've got one rising edge here, so this shows one full period of this signal. So we've got 1, 2, 3, 4 milliseconds is the period of our signal. So real quick, who can do the math? What's
250 hertz.
okay? You can't answer any more questions.
Round nose, overachieving student.
Yeah, I think Randy's question is, how do you know it's not 255 hertz? Like
Right. Well, and I'll get there.
okay.
But yes, so that tells us, you know, in the perfect place, and that's what he's got. Maybe I should have drawn those not on my green lines. Oh well, then I get to go and
Simple.
rebuild my lines. Okay, so that's one thing. Oops. Too many markers, not enough brain cells. So now let's say he's got his ideal signal, 1,000 hertz, so it would come like this. That would be his ideal signal.
That's 500 hertz, actually.
No signatures.
Oh, okay.
Here you go.
500 microseconds per division.
Happier now? Thank you. Okay, that's his ideal signal. As it turns out, he goes and looks at this with a scope, and he discovers that his signal is actually kind of doing this number. Well, this is hard to make it actually look right. But he discovers that he's not quite making it all the way over to these divisions. So this is actually taking less than a half a millisecond, or 500 microseconds, per division. So now he knows immediately, okay, it's faster than I expect. So what he'll want to do